Have you ever thought about how everything you see, stars, planets, even you, is made from just a handful of tiny particles? But here's the real puzzle. Where did those particles come from? Let's focus on protons, the essential building blocks of all atoms. How did they form from nothing? To unravel this mystery, we need to travel back, way back, to the first moments after the Big Bang. 13.8 billion years ago. The universe began not with an explosion in space, but with an explosion of space itself. It was an incredibly hot and dense environment, brimming with energy, but no protons existed yet. In those first fractions of a second, the universe was a chaotic quantum soup, where particles and antiparticles flickered in and out of existence, thanks to Einstein's famous equation, E equals mc2. As the universe expanded and cooled, this energy began to condense into matter. The first players on the cosmic stage were quarks, the fundamental building blocks of protons and neutrons. As temperatures dropped to around 1 trillion Kelvin, quarks started to bind together, forming protons and neutrons, held tightly by the strong nuclear force. This process, known as quark confinement, occurred about 1 microsecond after the Big Bang. Protons, made of two up quarks and one down quark, began to emerge. But here's where it gets interesting. According to physics, for every proton created, an antiproton should also form. Yet, we find ourselves in a universe dominated by protons, with almost no antiprotons in sight. This imbalance is called baryon asymmetry, and it's one of the greatest unsolved mysteries in physics. Where did all the antimatter go? Did it annihilate with matter? If so, how is there any matter left at all, including us? Some theories suggest that a slight bias in the physical laws favored matter over antimatter, a tiny violation of symmetry. Others propose that unknown processes in the early universe tipped the scales. Now, you might wonder if protons can still form from nothing today. Technically, yes, but only under extreme conditions. In high-energy particle collisions, like those in the Large Hadron Collider, we can create quark-gluon plasmas and even witness new protons forming. However, creating protons from pure vacuum? Not quite. Even in empty space, quantum fields are fluctuating, but forming a full proton requires immense energy and specific conditions. So, in modern terms, nothing isn't truly nothing. It's a bubbling quantum field full of potential. Here's another fascinating aspect. Protons are incredibly stable. Unlike many particles that decay in mere seconds, protons can last longer than 10 to 34 years, far longer than the age of the universe itself. This stability is crucial because it means stable atoms can exist, leading to long-lived stars, planets, and ultimately, life. If protons were even slightly less stable, our universe would be a mere sea of radiation. So, how did protons mysteriously form from nothing? Energy transformed into matter. Quarks emerged and bound together. A subtle asymmetry favored protons over antiprotons, and these particles became stable enough to form the atoms in your body. This process wasn't random. It was governed by fundamental laws, yet it remains shrouded in deep mystery. Why is there more matter than antimatter? Why do these laws function at all? From a sea of nothing came everything.